you can definitely get a voltage gain out of this guy. Definitely. And if your output resistance is less than your input resistance, you're going to get a current gain out of it too, right? Even if it's the same, you'd still get a current gain because your output voltage is higher than your input voltage. And of course, out of an amplifier, what type of gain are we ultimately shooting for? Come on, guys, I know we talked about that last class. What gain are we actually shooting for out of an amplifier? Power. Why power? Because that's work. I mean, we go out and buy one for our car. We don't call it a voltage amplifier. We don't call it a current amplifier. They call it a what? A power amplifier. That's what you're trying to get, power gains, because power gain is work. Now, of course, we can get power gain different ways. The amplifier can give us a voltage and a current gain. Or if it gave us a voltage gain, we would still get a power gain, right? You understand? So if we get more volts out than we get in, then we'll get a power gain. We can have a current gain. And that's the difference between these amplifiers, is that a common collector, a common emitter will give you both a voltage gain and a current gain. A common collector will only give you a current gain. And then a common base will only give, what did I say? A common base will only give you a voltage gain. I had to think about what I was saying. And each one of them has a use. Probably the least used amplifier is the common base. The two most used is the common emitter and the common collector. So we won't get into very much detail. Your power amps. When you drive speakers, you're looking for current, because how much bump you get out of a speaker depends on how much current you put into those coils. So common collectors are used for current gain. We can get a ton of current gain out of a common collector. It's still documented as me using it when it kicked off. So I gotta go out. Hold on a second. Get rid of this guy. That won't let me delete it, so I'll have to restart my computer. So I'll just open it up as a if I don't save it as something, it won't let me write on it. It won't let me modify it. Okay, guys, y'all think y'all can? So that's what we're going to do. We're going to learn the characteristics of these different amplifiers, and of course, that would give you an idea of what you're going to run into. Okay, guys, can y'all calculate this guy? Of course, how much gain we're going to get. This is not going to be a good amplifier. Why? So right now, it's only going to have a gain of what? 1. And if I load it, it's going to have a gain of less than 1. That's a very, very poor design amplifier. But it works out good for calculations. So what's the first thing we're going to calculate? PV, good. probably use what formula? Probably call it, you don't have to use it, but it saves you some steps, because most of the time you can do this in your head, right? So the voltage divider formula says what? It says VB, which is going to be equal to VR1, would be equal to what? Yeah, 32K over 10K. Got me messed up. Yeah, I got it. I know. I know. Thank you. 10K over 32K. Of course, you can drop the K. Why? Because it's on the top and the bottom. And then we multiply that by what? 30. We call this the voltage divider formula. It works out really slick. I wish they really make sure they need to teach this in DC. So VB would be equal to what? What's that? 9.1? Okay, I think say 9.1. 4.1? Okay. What do we do now? Yeah, we move over to VE. Good. So VE would be equal to 9.1? 9.4? Okay, sorry. That's why I kept hearing 4. Okay, so what would VE be equal to? Yeah, good. Minus 0.7. Good, guys. So in DC, all your resistors did was drop voltage, right? Consume power. That's all they did. But what we're trying to do is to set you up for when we actually start adding these things to active components. So what we got for VE? What's that? Okay, so what we know now? So now what will we calculate next? IE, right? Be equal to what? 8.7 divided by 1K. What does that give me? Yeah, 8.7 milliamps. Then what would be the next thing I would calculate? VC, right? Well, we can't calculate VC yet. What we need to do is calculate VRC. Okay, so we'll calculate VRC is going to be equal to 1K times our emitter current, because even though they're not the same, they're so close it won't give us any problems, right? So what we got? .7 volts, right? 1 volt per milliamp, which we should have expected because this guy here and these guys here is the same size. They get the same current. Then I would calculate DC. Now I can calculate DC. So what I'm going to take is I'm going to take 30 volts. I'm using Kirchhoff's law minus VRC 8.7, and this is going to give me VC. So what's VC? What's that? Okay? And then I can calculate VCE, which is very important. What does VCE tell us? It tells you what region the transistor is operating in. If this comes up to be less than a volt, we say it's what? Saturated. If it comes up to be equal to VCC, we know it's cut off, right? If it comes up to be in between the two, we know it's in the active region. So I take VC, which is 21.3, I subtract from that 8.7, and this gives me voltage collector to emitter. And by George, this is, and you can you can measure this voltage even if it's active, because these audio or these waves are coming in. They're going to be composite sine waves if it's audio. And what's the DC average of a sine wave? It's 0, right? You understand? So even though this is coming up here doing this, my meter's still going to put it right on top of the bias. So you can measure the bias of an amplifier even when it's operating. If the bias is right, then the transistor's doing what it wants to do. If the bias is wrong from what you anticipate, then something is wrong. That makes sense? But if you don't know what the bias is in the first place, then you can't even tell if it's right or wrong. Because just because you measure a voltage on the base, if it's the wrong base, then the transistor is either going to be biased toward cutoff or going to be biased toward saturation. We'd like it to be biased right down the center, right? And of course, that's almost never, because we set the bias with these resistors, and odds are we're going to use standard resistors. When you calculate the amplifier, you don't come up with standard resistors, so you're either going to have to move it a little bit toward cutoff or move it a little bit toward saturation. And this is what happens. So right now, this amplifier looks really good. But I have the dang thing turned down as low as I can possibly turn it down. So what I'm going to do here in a minute, I'm going to start raising my input and get my input higher than what we got. And you see right off the bat, you can see what happens. So up here at the top, this is cut off. So it turned that transistor off as far as it could turn it off, right? And once the transistor's dropping all the voltage, there's no more voltage left. So what does it do? Well, it clips off the top. When we come up here and look at the bottom, you see it's also clipped at the bottom. Now, if the amplifier was designed perfect, it would clip at the top, it would start clipping at exactly the same end. But down here, the transistor's turned all the way on, and once it's turned all the way on, we can't turn it on anymore, right? You understand? Notice the input, when it goes high, when it's going up, the output is going down, because we're taking our output across the transistor. When the input goes up, the transistor turns on more, and we're taking the output, its resistance goes down. And what happens when resistance goes down? Well, the voltage drop across that resistor is going to go down, right? You understand? So one of the traits of a common emitter amplifier is that the input and the output are 180 degrees out of phase. Can you see that? So when this has a positive alternation, my output has the negative alternation, right? And when my input goes negative, my output is going positive. So that's one of the other characteristics of a common emitter amplifier. You get a 180 degree phase shift going through it, which in stereo doesn't mean anything as long as your left and your right channel has the same number of phase shifts, right? So that means you're still back in phase, you're still phase as far as your ears go. But if I bias it wrong, if I bias it toward cutoff, then I'll start raising my input signal, then the tops will start clipping first. If I bias it towards saturation, then the bottoms will start shifting first. And that's going to set, where it starts clipping, that's going to set your maximum input voltage, right? You understand that? So if you got a gain of 10 and you're shifted 1 volt up toward a cutoff, then it's going to limit how much input you can get in before your amplifier starts clipping or distorting the actual signal. I think I got a cord in my phone. I'll let y'all see. This guy here right now wouldn't work real well with audio. It'd work real well with audio, but we can't use this to drive a low impedance load. So speakers are very low impedance. So we can't use we could use this to drive another amplifier, but we can't use this to drive a speaker. We'd lose our gain. That's where the common collector comes into play. Y'all guys go ahead and take a break. That's where I wanted to be. This is, so I got this is audio right here. It's not noise, it's good. That's what it is. So this is what audio looks like. So you can see why if we troubleshoot these things, we like to use, because how can you get the gain of this? Because it's what? It's all, this is just one channel too. Now this is the output of my phone, but it's all over the place. And of course the big frequency, that's your bass and all your trebles and all your, they're all composite together, right? And of course usually when you look at the, Toby Mac. So the basses are usually the same, and that's why normally when you hook up a power amp, you have a bridge or bass because it's the same in both channels anyway. So basses don't split up; it's your other ones that split up between left and right channels. So you can see this would be really, really hard. I mean, we could tell if we get gain, but we couldn't tell how much gain we got. But if we was to take a function generator and put it in, then now I'm looking at a sine wave, right? And of course, we'll look at what we call the actual frequency response of the amplifier. So an amplifier has a certain frequency, has a certain bandwidth. You don't know what a bandwidth is? I know you'll hear it all the time, but what does bandwidth mean? I mean, you hear it all the time. When they start talking about internet access, they start talking about broadband and all that kind of stuff. You know, they give you more bandwidth and so, you know. So what is bandwidth? Anybody know what bandwidth? Yeah, when we send information, we're sending it to a media, and bandwidth is the range of frequencies that a media can reliably pass. So these amplifiers have bandwidths, and we'll show y'all. We won't really get in a lot of detail on that. So if my frequency gets down too low, my coupling capacitors start adding a lot of opposition, right? You understand? If my frequency gets up so high, then literally it bypasses the transistor. The transistor acts like it has what we call an input capacitance. And the higher the frequency, the lower the X sub C is. So sooner or later, it's going to bypass the emitter base junction and you lose all your gain. So transistor amplifiers have what we call a bandwidth. And if you exceed the bandwidth, you know, and that's part of your design is trying to pick those capacitors. The bigger the capacitor, the better the bandwidth, but the better the higher the frequency, but the more it's going to cost you. Does that make sense? And that's what you're trying to do. You're trying to shoot for a happy medium. So this guy right here. So if the frequency gets down too low, if you get it down too low, it's going to block it, right? Because the lower the frequency, the more it starts looking like AC. And anybody know the formula for calculating that, how much opposition that guy has? How many of y'all had AC? How do we calculate the opposition of that guy right there? So right now we're using a 1 microfarad capacitor, and we got, I don't know, we got about 1,000 hertz. So right now, X of C would be equal to 1 over 6.28 times the frequency, which is 1,000. And what we're using 10 microfarad capacitors times 10 mic. So what would be the opposition that guy offers to my AC signal? .28 times 1,000 times 10 micro, and then take the reciprocal of that. Anybody got it? What's that? 15.9 ohms. So compared to 100K and 10K and 100K over there, at 15.9 ohms, it's not even there, right? You understand? But what happens if I was to drop that sucker down to 6 ohms? Well, see, now that capacitor, instead of dropping almost no voltage, it's going to start dropping voltage. So if the frequency gets down too low, that means that the signal's not even going to get into the amplifier to be what? To be amplified. So sizing these capacitors right here, these coupling capacitors, is very critical as far as setting the lower bandwidth of your amplifier. Well, what we have right here is we have a little old tiny capacitor that's between the collector, between the base and emitter, and we have another little tiny capacitor right there. Well, if the frequency gets too high, then these guys, their opposition goes down, and sooner or later that sucker is going to bypass, right? Your signal, instead of it's going to go up through the collector instead of going through the base. And so that would set your upper frequency of the thing. So the transistor determines the top frequency, and your capacitor determines the bottom frequency. And we've got a little thing, if you look at the data sheet, it's called FT, and that's what we use to calculate the upper cutoff frequency. And it's not easy, so we're not going to really get into that, but you could calculate, and this is what the engineers would do when they design it. All you need to realize that every amplifier that uses capacitors is going to have a bandwidth. And we do this a lot. They have a type of amplifiers they call direct couple amplifiers, but the problem with direct couple amplifiers, if one transistor goes out, it usually blows out all of them. Where if you protect each stage with a capacitor, you might lose one stage of amplification, but it don't affect the other one. So they're just a lot more reliable. Direct couple amplifiers have a lower bandwidth, where capacitive couple amplifiers would not have a lower bandwidth as good. Okay, got one more thing we'll look at, and then we'll go to lab. This is electronic workbench, but I couldn't get it to show me on frequency. I'm not going to say it, but it's really nice because what I did, I just set the circuit up myself. And then we went in and looked at it. The Q point of the circuit is where you bias. It's called the quiescent point. The Q point of the circuit is where we bias it at. So right now, this guy, if we got the way you do it, of course, down here, this is your VCC. This right here would be cutoff. This over here would be saturation. So if we got 0 volts collector to emitter, that means it's saturated, right? If it's dropping VCC, it means it's what? Cutoff. Now, if we're going to amplify, if we're going to operate this as an amplifier, we want it to be somewhere in the center. So what we do is we take the saturated current, which would be right here, and we take the cutoff voltage, and then we draw a line between the two. And where would I want to bias this thing at if I wanted to operate it as an amplifier? I would want to put it right in the center, right? You understand? So what this would tell you, it would tell you, all you do if you drew a perpendicular this way and that way, it would tell you what collector current you need to do what? To bias it in the center. So these guys, and then I could come over here and put AC on this thing. Then that would come over here and would tell me that my input would swing between this voltage and this voltage while it was operating. And that's what's nice about these characteristic curves. But unfortunately, they don't give you that. But they give you the beta, right? You understand? So you could develop your own characteristic curves. So are these good readings or bad readings? So is it everything okay or is it bad? So what do you need to do? You need to figure out what they're supposed to be. If they're what they're supposed to be, then it's good. And then if you're not getting any signal out, if the bias is correct, it means if the bias is where it's supposed to be, it means the amplifier is okay. So now you're going to look somewhere else. It might be the stage before the one, right? You understand? Or you might not even have the signal in at all. You know, an amplifier can't amplify something if it's not there. So are these voltages right or are they wrong? Nobody's figuring this out? And what's nice, what didn't we use to calculate all these voltages or anything? What didn't we use? We didn't use beta. Now, what's the problem with using beta? It changes with what? Temperature. But what we're going to find out is that we set the beta of the circuit. All we know right now is it's somewhere between 30 and I think it could be as high as 300, right? Now that's what's nice about a voltage divider bias is that once you set the beta of the circuit, then it can't change with temperature. So is the base voltage supposed to be about 3.1 volt? Huh? What's it supposed to be? I calculate 3.19 volts. They're measuring 3.13. Is that what y'all got? So is that good or bad? Nah, that's good. Because remember, we're doing perfect calculations, but these are not perfect resistors. Are we okay? You okay, Truth? Huh? I came up with 3.19 or 3.2. I came up with 3.2. So that's 4.7 K. We can drop the K because we got K divided by 14.7 K. Add two together, multiply this times 10 because we got 10 volts applied, and it comes up and gives me 3.2 volts. You okay? So what you did wrong? We divided by 14.7. Where'd you get 5.7 at? If I had 10K, this is 10K, it's not 1K. That's 10K. So we calculated 13.2, 3.2, we got 3.13. Then I'm going to come up here and subtract 7/10, but I can see over there already that that looks pretty good. So we calculated, I didn't do that. We calculated 3.2, and then we're going to minus points. Dang it. About 3.2. Dang it. Calculates to be 2.5 from perfect, and it's 2.4. That's okay. And then we calculate emitter current. So this is the measurements we should have if this amplifier is working correct. Right? So here we go. Here now we're measuring 10 volts across from the collector to a common. What's the problem? What's the problem, guys? What could be the problem? R1 could be open. Probably why R1 could be open because this is where the base current comes from. This is where our bias base current comes from. So it flows up and through there, right? You understand? Of course, we have two currents over here. We have this one and this one, but this is the base current flows there. So if R1's open, this guy will cut off. What else could it be? What about RE? If RE open? Now, how would I tell if R1 was open? So I come over here, I measure 10 volts. Okay, you understand? And then I come down here and I measure 3 point something. I couldn't measure that. Let's say I measure 0 volts right here, or some voltage right there, but it's going to be a lot lower than what it's supposed to be. And then I come over here and I measure 0 volts right there, then we know what. You understand? Oh, here's the measurements. So this is telling us what we would measure. So if RE was open, we would measure 10 volts right here, right? If R1 was open, we'd measure 10 volts right there. Now R2 could be shorted, but I've never seen a shorted resistor. Now I've seen one be shorted around. Somebody screws around, you know, and drops a piece of solder, or they don't clip their leads right on the back of the resistors and they touch it. So one of these has got to have a problem. Which one's got the problem? So they're the same trend. They're the same circuit. Okay, we got these measurements over here and this measurement, and they tell it. Dang, I need to take that. I need to block that out. What I need to do is click on it and it opens it up. Is this the same one we had before? 10K, 4.7K, 1K, 2. Yeah. So here, notice what we're doing. So we came over here and we measured this. What does that say? This means it's saturated, right? Now see that. Now we come over here. This measures the same because it's saturated. And this is wrong, by the way. When a transistor is saturated, it cannot drop 0 volts. It cannot drop 0 volts. So these will never, if these are the same, if these are exactly the same, then the transistor shorted, emitter to collector. Okay. So we come over here. This is supposed to be what? Supposed to be what? Now, why did it go down? So it's supposed to be 3.1. Okay, they're saying the transistor has a beta of 300. Right, you understand. So my bias over here is seeing this circuit, right here. And then it's seeing this, and then it's seeing that resistor over there. Now, normally, if it's got a beta of 300, the bias on this side between R1 and R2, it sees this resistor as 470 ohms times 300. And what's 470? So the base circuit sees the emitter circuit as times beta. Y'all understand why? Because we get the current gain of the transistor. So what size resistor is that? What size does this base see this emitter resistor at? It sees it at what? So what the actual circuit comes up being is it comes up being this circuit right here. 141K in parallel with a 4.7K, right? Then in series with a 10K. Now, we call it the rules of approximation. In a series circuit, for approximating, if I've got two resistors in series and one of them is 10 times bigger than the other one, for approximation, I ignore the small. We call it the 10 times rule of approximation. Over here, 10 times that would be 40K. This guy over here is 141K. So when I calculate this circuit over here, I ignore that resistor right there. Why? Because it's so big, it has little effect on the parallel circuit. So that's why when we calculate these guys over here, we ignore that resistor, because this resistor is seen as times beta. So what happens is this guy right here opens. As soon as that guy right there opens, beta's gone. So what happens is now this circuit is this circuit right here. 10K, and this is 470 ohms. In 4.7K in parallel with 470 ohms. So who are we ignoring now? We're ignoring this guy. Because this guy here is 10 times bigger than that guy. So this is the guy that's setting that is setting the base voltage now. Not the 400, not the 141K, because as soon as RC opens, what happens? And that's what this has always popped up. People say, well, if this opens, why did this drop down to 1.1 volt? Why didn't it stay in 3.7? Why didn't it stay at 3.2 volts? Why didn't it stay at 3.2 volts? Well, as soon as the collector resistor opened, we lost what? Yeah, we lost beta. So if we lost beta, then that resistor is no longer seen as what? Times beta. It's seen as the actual resistor. And now it's seen, we could probably calculate this. So what would the voltage be now? So what would be this is up here is 10K. So this would be 470. We're going to ignore that guy because it's 10 times that. And we're going to divide that by 1,470 ohms and multiply that by 10 and see what you get. See if it don't come out to give you about 1 volt. I can see it's going to be close to 1 volt because it's 470 on top and 474. So what does it give you? Huh? I can't give you 3.1. It was 3.2 when I used. It was 3.2 when I used a 14. So when we did this, so, huh? Oh, let's see what that looks like on that. So a while ago, we took 4.7K. I'm giving it to you wrong is what I'm doing. This guy here is a 10K. In my head, I saw it as a 1K. Because I knew it couldn't be the same thing because, understand what I'm saying? So before we said a 4.7K divided by 14.7K, right? Now we're going to say 470 divided by 10,740. Let's see what, yes or no. Y'all understand what we're doing? I knew it couldn't be 3.1 because that's what we got before we lost beta. So I knew I had to be doing something wrong. So what does it go to? Should go to about this right here, about 1 volt. Huh? Yeah. I thought it would be more than that. But what we're trying to do is we're explaining why did this change? Why did it change from 3.2? Why did it change down to 1 volt? Because we did what? We lost beta, so it drops way down. Yeah, the 1.1 volt would surprise me. Because when we calculate this, we ignore this resistor over there, even though it's part of this circuit right here. So this resistor is in parallel with that right there, but it goes through the transistor. And this resistor over here is seen times beta, right? You understand? So it's seen, if the beta is 300, it's seen as 141K. And if I've got 141K in parallel with a 4.7K, then what can we do to approximate the resistance? We just ignore the big guy, right? So in series, what do? The 10 to 1, the 10 to 1 rule. We ignore the little guy, right? Parallel, we ignore the what? The big guy, and it's called the rule of approximation, the times 10 rule of approximation. And we're definitely going to do a lot of approximation in the circuits because beta is going to be something, right? You understand that? So just because we say that, we could calculate the beta, but what we'd have to do to calculate the beta of the circuit is we'd have to calculate our input current, and then we'd have to calculate our output current. And then if I know my IC or IE and I know IB, then I can calculate the beta of the circuit. All I know is that somewhere my beta of my circuit is going to be somewhere between beta minimum and it's going to be somewhere between beta maximum. But on a voltage divider bias, once the beta of the circuit is set, it will not change. Because if the temperature tried to go up, it would try to make this resistor here drop more voltage. But that resistor can't drop more voltage because it's biased at 3.2 volts, right? You know, the base is set at 3.2 volts. So that the emitter current can go up. If the emitter current tried to go up, then this resistor here would drop more voltage. Which means this voltage wouldn't be 0.7 of a volt, which means the transistor would do what? It would try to move toward cutoff. So all we know right now is they're giving us 300. All we know that the beta of this amplifier circuit is going to be somewhere between what? Beta minimum and beta maximum. But once you set it, it's going to do what? It's going to stay there, right? You understand? Because this is going to be at 3.2 volts. Well, what if the current goes up? Well, if the current goes up, instead of this being, what was it before? I don't remember. It's going to try to go up. Well, if it goes up, this voltage is going to try to drop below 0.7 of a volt. Which means the transistor is going to do what? It's going to cut off, right? Well, what if this current tries to go down? Well, if this current tries to go down, this right here is going to try to become more negative, which means it's going to turn this guy here on more, which makes the transistor is going to come up until it drops 0.7 of a volt lower than that right there. So if this voltage tries to go up because collector current goes up, it can't go up. Why? Because the base is clamped at 3.2 volts, right? Y'all understand what I'm saying? So if this guy here tries to drop more voltage, so let's say what is it? 3.1, it's 2.7. Is that right? 2.5. Well, if this current tried to go up, this voltage would go up. Well, the voltage, let's say it tries to go up to 3 volts. Well, if it goes up to 3 volts, I no longer have 0.7 of a volt between my base and my emitter, so what would the transistor do? It cut off, right? Of course, it's never going to do that because it's going to sit there and regulate, right? Well, let's say that this tried to go down. Instead of 2.5, it tried to go to 1 volt. Well, now we're dropping almost 2 volts between the base and emitter, and it can't do that, right? You understand? So the transistor is going to cut on more to maintain what? To maintain that 0.7 of a volt drop between these two resistors. So if beta tries to go up, it can't go up. If beta tries to go down, it can't go down because we got the base locked at a certain voltage, right? Does that make sense? So this guy right here is totally stable until we burn it up. This guy would basically regulate until we froze it solid, or until we burn that transistor up, it would regulate that current. I mean, the bias. Then what we do is we bring our input signal and we let it change that, right? It's either going to do what? It's either going to add to it or subtract from it. But it will never drop down where we lose that 0.7 of a volt right there. Because if we drop below the 0.7 of a volt, the transistor would cut off, right? And that's what I was doing a while ago when I was overdriving the thing. I was literally causing it to saturate and cut off. And that's what's so neat about the voltage divider bias, is that it's just as stable as a rock. So once I calculate, if I knew my input resistance, I knew my input voltage and my input resistance, then what could I calculate? I could calculate my input current. And then if I know my input current, I know my output current real easy, right? You understand? Then I could take IC or IE divided by IB, and that would give me the beta of this circuit. But right now, all we know, of course, they're giving us the beta. So we're not going to go through all that stuff. So normally when I give you the beta, I'm going to give you, I'll give you the beta of the circuit. Not the beta of it's the beta of the circuit, right? You understand that? Because the beta of the transistor can actually be anything. But what we're doing with the circuit is we're setting the beta of the transistor. And once the beta is set, it can't do what? Can't change. So this is what happens over here if R2 opens. So where's R2? If R2 opens, the transistor is going to saturate. Because that 3.1 volt, that 3.2 volts now has the ability to go up. So now instead of this resistor setting the base voltage, this resistor is setting the base voltage. Right? You understand? So what happened to the base voltage? It went up. Well, if it went up, notice your collector voltage, we're expecting this to be 4.8, but look where it's at. So what did it do? It moved toward what? Saturation. In fact, it'll saturate. The input signal will bring it out of saturation because it'll subtract from it, but it'll definitely saturate. It'll be clipped on the bottom. And we could do this real easy. We could put these over here. So what are we going to do on the first one? So let's look at ours. And then we'll go to lab, guys. We need to do some lab now. So this is the one we have set up, right? What did we calculate here? Y'all got them down? What's this supposed to be? Anybody got it written down? So we're fixing to simulate some open circuits. So this guy's supposed to be at 1.8. This guy's supposed to be at 1.1, right? And what's VC supposed to be? And we're going to show y'all something too. So what we got for VC, anybody remember? Come on, come on, come on. Let me hook up my stuff real fast. I took my power supply off. So that, now I understand what we're doing here. So I need my power supply. Power supply. I was going to hook my phone up to our little amplifier, but I couldn't get it to work, and I just realized what I did. I took the ground off on my power supply. So what we got? What should we measure for VC? Uh, 11 volts. Yeah, yeah, so VC is going to be VCC minus that, right? So we got this thing, I've got it operating again, I think. Let me find my other scope probe. This guy here up to the output. Oh yeah. So I'm gonna leave the signal coming in here, and we're gonna come in here, and I'm gonna let me bring up my camera. I'm gonna take my camera and put it on my meter. I'm gonna turn my meter on. I don't see another jumper. Normally I like to hook up my meter. So here's dB. I measured 1.39. We calculated 1.8. Here's DE. It's going to be 0.7 volts. All right, we calculated 1.1, but we're a little low there. And then my voltage on my collector is right here. It's 9.1 volts. Okay, so what I'm going to do, we still have our scope hooked up. So this is what's going on. Here's my input. Here's my output. We can see the gain. We can see the 180 degrees out of phase. So guys, which one do y'all want to open? Okay, R1, that's our bottom, that's our top resistor, right? So we're off on R1, we're going to open up the 100K. So I'm going to come over here. Here's R1. Oops. Y'all can't see me. So here's R1. I'm going to just come up here and disconnect one side. My amplifier does this. But we can see we definitely got a problem. We still have an output. And what you have to understand, this is AC. AC will couple through almost anything. So it's very seldom on the output of an amplifier, even if it's totally cut off, that you're not going to get something through it. So can y'all see it? So here's what happened to my output. Now let's look and see what happened to our bias. So here's my base voltage now. Oops. Need another camera. So here's my base voltage. Oops. Make sure it don't touch. Here's my base voltage. What did it go to? Oops. It's focusing on my hand. Sorry, guys. So here's my base voltage. It went to what? 0. Okay, here's my collector voltage. Okay, so here's my collector voltage. Something's going on. What's that? That's why our voltage. What was our voltage we supposed to have on this? That's the problem right there. It's supposed to be 20 volts, right? That's okay. We'll leave it like that. So 16.5 volts. That's why our other voltages were a little low, by the way. And so there it is, 15. So, you okay? What are the voltages y'all want to measure? Here's our emitter voltage. It's measuring almost 0 because the transistor's cut off, right? We okay? Okay, what do you want to open now? Let's open RC. So here's our base voltage. It's going to drop down a lot because we lost beta, right? See, so that was wrong. It's dropping down to about 300 millivolts. We calculated 800 millivolts a while ago, But remember, my voltage is not at 20 volts. Let me set it to 20 volts. Now I hit it with my, oh, I can't do 20 volts. This is all we can get out of this one power supply. So we should have calculated for that, but that's okay. So with 20 volts, we calculated, the book says 1.1 volt. With 20 volts, we calculated if we lost the resistor, it was going to go to what? 800 millivolts. So it's actually sitting here at 300. So I hook the resistor back up. It goes up to 1.3 volts. I take the resistor down, it goes to 300 millivolts. Here we have beta. Here we don't have beta. Y'all understand? And that was a big problem we had in, even when I figured out what was going on. You know, why did that drop down? Because when we calculate it, we ignore that resistor over there anyway. But we ignore the resistor when it's active because it's seen as times beta, right? You understand? Collector voltage should be pretty close to 0. Emitter voltage should be pretty close to 0. And that's with what resistor open? Now we're going to open our R2. It's going to drive the transistor towards saturation. Got to keep it from touching. And we look at so if we look at our amplifier, see it's the bottom's clipped off. You see that? Now we got it on AC couple, so undoubtedly it's on AC couple. I didn't expect that. Here's my base voltage, so it's going to go way up. So now it's, well, not way up. So a while ago it measured what? Here's with the resistor in there, it's measuring 1.38. So it went up to, can you see that? Oh, no. Yeah, so it's gone up to about 1.9. So it went from 1.4 to 1.9, half a volt. Which means my collector voltage is going to go down. So if my base voltage goes up, my collector voltage is going to go down, right? You understand why? So here's the collector voltage. It was at what while ago? It was 8 volts, wasn't it? Yeah, 9 volts. Now it's at, okay. Then when I measure the VB, it's going to go up too. So it's at 1.2 volts, and it was down less than a volt while ago, right? So what we're trying to demonstrate is that we got a problem with our amplifier, and one of the first things we do is we check the bias. If the bias is right, then that amplifier is okay, right? You understand? If the bias is wrong, then you should be able to determine by the bias which component inside the circuit is wrong. So if RC goes up, we know the transistor is moved toward saturation. It's moved toward cutoff, right? I said that wrong. If VC goes up, we know the transistor is moving toward cutoff. If VC goes down, we know it's moving toward what? Saturation. If it goes up, it means either the base voltage had to go down or the collector current had to change. If it goes down, it means the transistor had to be moved towards saturation, which means RE had to get bigger. So if RE gets bigger, right, you understand, right? If RE gets bigger, it's going to drop more voltage. If RE goes smaller, then, we're going towards saturation. If RE goes down, then it's going to move it towards saturation. If RE goes up, then it's going to move it toward cutoff. If VB goes up, it's going to move it toward what? If VB goes up, it's going to move it toward saturation. If VB goes down, it's going to move it toward cutoff. Oh, well, we might let y'all play around with electronic workbench because this is the name of the game. We're not going to teach you how to design an amplifier. What we're going to teach you is how to know what these biases are supposed to be. And then if you measure them and they're right, then the amplifier is okay. If you measure them and they're wrong, then you need to know what component inside that amplifier is bad. We could also have a problem with this too. Let me hook the circuit back up. And what I'm going to do is I'm going to do this. Let me hook up. So what I did is I put too much input signal into the amplifier, and we're going to come up here and measure our bias now. What would you think? Would you think the bias would be the same, or would you think it would be different? It's going to be different because now, right, y'all understand. So now the input is actually saturating the transistor and cutting it off. Before it wasn't doing that, right? So let's look and see. So here's my base voltage. I'll just tell you what it is. So it's measuring 0.3, and it's supposed to be what? It's supposed to be 1 point something, right? So what happens if and this is something you got to consider, and this is where a scope is really going to tell you a lot about what's going on. So if you're going to troubleshoot audio equipment, your two tools you need is you need to see about getting an oscilloscope, and you need to get, because this appears like we have a problem with one of our resistors, right? But the problem is it's the amplifier is doing all it can do, and what's causing our bias to be wrong is what? Is the input signal is no longer a sine wave. And if it's not a sine wave anymore, or a composite sine wave, then the average voltage is no longer going to be zero. If the average voltage is no longer zero, then it's either going to add to the bias or it's going to subtract from the bias, right? Y'all understand what I'm saying? That makes sense? So usually the first tool we do is the first tool we do if we got a problem is we look at it with an oscilloscope. And the oscilloscope will show you a lot. Because if you get this garbage right here, then that means it's going to screw up your bias in your amplifier. Are you okay? So oscilloscopes are not cheap. And hopefully if you work for a company where you do this kind of stuff, they usually furnish that. I have my own oscilloscope at home, but I can't even tell you the last time I turned it on because I don't do much of this stuff anymore. And we've got all this stuff here when I'm here. I don't even know if my oscilloscope, there used to be a company called Heathkit. You remember Heathkit? Heathkit sold kits of just about anything. And it was a kit, and they sold TVs. Yeah, they sold TVs, they sold oscilloscopes, they sold meters, but they sold it in kit form. And you put it together. A TV, an entire TV came as a kit. And you'd put that together. And man, you talk about learning something. Well, my oscilloscope is a Heathkit. It's Heathkit. So I got it as a kit and I put it together myself. Whether it still works or not, it's out in my shed somewhere. I can't tell you the last time I turned it on. But anyway, most of the time, if I'm gonna do any troubleshooting on stuff, then I'll bring it in here and do it. In fact, we got an amplifier in there that we can look at and see if we can figure out what's wrong with it if I want to later on. Nancy brought one in. It's in there, and I hadn't looked at it because I didn't have a jack that I could input a signal into it on because it uses a big phono jack. Of course, I could have took it apart and put it in there directly, but I'll show y'all that. But we're fixing to go to the lab. No, it's a